Okay, so we stopped yesterday with the statement of this theorem, so I wanted to begin today by proving this. So going through, first of all, everything that's said here. So this is solving linear congruences, and as I mentioned yesterday, this relies on our statement of theorem 3.1 in chapter 3, which had to do with linear Diophantine equations. So we'll see immediately in the proof of this how this relates to theorem 3.1. But looking at this, so if m is a positive integer, a and b are integers, a is not 0, then we look at this congruence, ax is congruent to b mod m. So I want to solve this thing, right? So we already saw a bunch of special cases where this was immediately solvable and exactly what happened in those cases. But in general, I want to talk about solving this thing. So it turns out this has a solution if and only if The GCD of A and M is a divisor of B, and in that case, there's exactly D solutions that are distinct mod M, right? So remember, when you're solving these congruences, there's the potential for you to get more than one solution mod M. Of course, there's also the potential for there not to be a solution. So yesterday I showed quick examples of so 3 examples of every case happening, right? A single unique solution, a list of some solutions, and then no solution. So all those are possible here. So anyway, in the event that the GCD of A and M is a divisor of B, then there's exactly D solutions that are distinct mod M. So in this case, if X naught is any solution, so if X naught is taken to be a particular solution to this congruence, then all the solutions mod M have to be of this form. So they're any particular solution plus M over D times K, where K runs from 0 up to D. Okay, so K is strictly less than D here. And then to actually find that particular solution, here's how it is done. The particular solution X naught satisfies the following congruence, so it's A over D X naught is congruent to B over D mod M over D. Okay, and so we'll see how that works. So this is a lot is said here in this statement. So the proof is not too long, but it's I'll say longer than typical for the proofs in this class. It's about a page long in the textbook, which, as I said, is a little bit longer than is typical for our proofs. Okay. So this, as I mentioned, is actually related to Theorem 3.1 from Chapter 3. So first, let's rewrite this congruence. So we have the congruence AX is congruent to B mod M. But of course, this statement is equivalent. So this is really, when I write this, I mean, it's a loose thing. This means is equivalent to. So this is, or has a correspondence with. So AX is congruent to B mod M is equivalent to AX is B plus MY, or rewriting this, AX minus MY is equal to B. Right. So going in either direction here, so having this relationship between A, M, and B, and having the congruence AX is congruent to B mod M, this is, these two things are equivalent. Okay, for some integer y. Okay. So once I have an expression that looks like this, now you might see why Theorem 3.1 comes in. So maybe we should remind ourselves what Theorem 3.1 stated. So flipping back through the textbook here it is. So Theorem 3.1. Assume that A, B, and C are integers where at least one of A and B is non-zero. Then this equation, this linear Diophantine equation, AX plus BY is equal to C, has a solution if and only if the GCD of A and B is divides C. And if it has one solution, then it has an infinite number. And if X naught, Y naught is any particular solution, then all solutions are of the form so the X is X naught, the X slot of our particular solution. So it's X naught plus B over the GCD of A and B times T. Y is Y naught minus A over the GCD of A and GCD of A and B times T with T some integer. Okay. that's reminding you what Theorem 3.1 says. So, I want to use Theorem 3.1. So by Theorem 3.1, this equation has no solution if D does not divide B, where D is GCD of A and M. So this is the terminology I'm using coming from the statement of this theorem 6.18. Okay. Now note there's some confusion with the theorem 3.1 as stated. Theorem 3.1 was stated in terms of A, B, and C. So replace the triple ABC in Theorem 3.1 with A minus M and B. So here, looking at this, in Theorem 3.1, the equation in question was AX plus BY is equal to C. So in this theorem, B is playing the role of C, and minus M is playing the role of what I called B in Theorem 3.1. Okay. Okay. So I should say to go from AX plus BY equals C to AX minus MY is equal to B. Okay. Okay. Now, so this has no solution if D doesn't divide B. Thus, we assume that D divides B. Now, if D divides B, then in this case, Theorem 3.1 says that any solution must be of the form, so any solution to, let's say, star here. So any solution to this equation star must be of the form x is equal to x naught plus m over d times k, and y is equal to y naught plus a over d times k, right, where k is some integer. Okay, and x naught, y naught is any particular solution to star. Okay. All right. So, thus, all solutions of the congruence AX is congruent to B mod M have the form X is equal to x naught plus m over d k. That's exactly what we were trying to show, right? So we were exactly trying to show this fact. Okay, we've also shown that, I should go ahead and say that by our theorem 3.1, this has no solutions if D doesn't divide B. And so it only has a solution if D divides B. In that case, we have shown this fact that any solution has to be of this form. So now we have one more thing to show, and then we have to show uniqueness, and that's it. Meaning that we have to show uniqueness of this expression, meaning that it truly has to be of that form. Okay. So what does it mean to say this? So this says that the solutions x are exactly the integers congruent to x naught mod m over d. This is actually just the definition of being congruent to x naught mod m over d. Right. Okay, so keeping track of what we have to prove in order to be done, I now have to consider when or whether two solutions are distinct mod m. Right. So lastly, I need to check when these solutions are distinct mod m. Nope, I'm off camera. There we go. Okay. Okay. So how do I do that? Well, this is a bit like checking for uniqueness, except I'm not quite checking for uniqueness in the sense of the solution to some equation. I'm checking for uniqueness or distinctness mod m, right? And so in order to do that, I suppose that I have two different solutions of the same form. So let x, oh, I've already used x naught for my particular solution. So let x sub 1 be equal to my particular solution, x naught plus m over d times k sub 1. And then, of course, another option is x sub 2 is x naught plus m over d times k sub 2. Okay. And so let these both be two solutions to star. Okay, similarly, or to my congruences. And suppose that x sub 1 is congruent to x sub 2 mod m. Well, just by definition of congruence mod m, this means that x sub 1 minus x sub 2 is equal to a multiple of m. So we'll say this is m times k sub 3 for some integer k sub 3, right? Okay, but in this case, right, x sub 1 minus x sub 2 is a multiple of m in this way. That occurs if and only if, where we have this expression for each of these things. So I can just plug that in here. So this is x naught plus m over d k sub 1 minus x naught plus m over d k sub 2. And that has to be equal to some multiple of m times k sub 3. Okay, so doing this subtraction, what do I get? I get m over d times k sub 1 minus k sub 2 is equal to m times k sub 3. Right, the x naughts cancel here, and this factors in that way. Okay, so then dividing both sides by m and multiplying by d, what I get here is that the difference of k sub 1 and k sub 2 is a multiple of d, i.e. k sub 1 is congruent to k sub 2 mod d. Thus, we get the distinct solutions mod m by letting x be of that form, x naught plus m over d times k, with k running through any complete set. What we mean by complete set of residues is you don't need d consecutive ones of them. You could pick and choose judiciously. So what I mean by complete is we understand that we could take the least non-negative residue in any case, mod d. And if you chose from a list of those in a way that exhausted the list, okay, so for instance, mod 3, your least non-negative residue classes are 0, 1, and 2. Okay, those are your representatives. So in that case, k would run through 0, 1, and 2. That's an example of a complete list. Another example of a complete list would be 1, 2, and 3, right? Because 3 is congruent to 0 mod 3. So running through 1, 2, and 3 is the same thing as running through 0, 1, and 2. Okay. Of course, we could be really stupid here and say instead of running through 0, 1, and 2 or 1, 2, and 3, we run through 1, 5, and 6, right? That would do it just as well. Okay. But anyway, we don't have to get too philosophical here. So with k running through any complete set of residue classes, mod d, sorry, i.e. just being as simple as possible. If we're taking the least non-negative residue classes, k is greater than or equal to 0 and strictly less than d. Okay. All right. So, i.e., there are d such distinct solutions mod m. Okay. So there's d of them. This is how we obtain them. Okay. And this is why there's d of them, because if we just count any complete set of residue classes, there's going to be d choices there. Okay. Easiest way to see that is only consider least non-negative residue classes. Okay. One more thing I have to tidy up here. So proof continued. One more thing to tidy up. Okay. So I need to show that our x naught always arises from solving the congruence that I've listed in my theorem statement, which is a over d x naught is congruent to b over d mod m over d. Okay. Well, rewriting that congruence, right, in terms of its equivalent statement, this means that a over d x naught is equal to b over d plus m over d times, say, z for some integer z. Okay. Multiplying through by d, this is true if and only if a x naught is equal to b plus mz, which just says that x naught is a solution to ax is congruent to b mod m. Right, that's the only way that happens. Okay. So that's it. So you saw there wasn't really anything deep going on with the proof here. It was just a whole lot of bookkeeping because the theorem itself was a pretty long theorem statement. Okay. So it's kind of long and somewhat annoying here to actually go through all of this. Okay. So what's one thing I can say immediately before I even do a single example? Okay, so here's an important fact. There is a very important special case of this theorem. Okay. Let's go back and have a look at our theorem real quick. So here's the full theorem statement. This theorem tells you exactly what is up with linear congruences, right? So if you have a linear congruence in this form, this theorem is basically telling you exactly what is going down here in terms of how many solutions you can expect. That is, how many distinct solutions mod m. If you're in the integer world, obviously you're solving a congruence, so there's going to be infinitely many solutions in integers. But we're just interested in how many solutions we get mod m. Okay, and so looking at this, whenever you're solving a thing, it's always nice to know when you are in the unique case, right? The case of having a unique solution. So in this case, that means unique mod m, right? And so the particular special case that's very important, that comes up very frequently, by far the most frequent of any special case of this theorem, is when d is equal to 1. It's when a and m are relatively prime. So d is equal to 1, and that means that you don't have to worry about d being a divisor of b because it's 1. So 1 is always a divisor of b. And in that case, you have exactly one solution's distinct mod m. So you have a unique solution mod m. Okay, so d equals 1 is that special case. So this is the case when d is equal to 1. All right, and so here's a corollary that is very important. It's going to be applied a bunch. So this is if the GCD of a and m is equal to 1, then the congruence AX is congruent to B mod M has exactly one solution mod M. Okay. So to see that, of course, just set d equals 1 in the theorem. So the statement is that 1 is always going to divide b, so there's definitely a solution. And then your distinct solutions are particular solution plus multiple of m, but k is only allowed to be 0. So you only get a single one. Your x naught, that particular solution, is the only solution. Okay, so that's the only one you get. Okay, I'm going to list a couple of quick examples, and then we're going to go over how we can actually solve one of these in particular. Okay, so here's a list of some examples here. So let's look at 6x is congruent to 7 mod 15. Okay, well, this has no solutions. Why? Well, the GCD of 6 and 15 is 3, but 3 does not divide 7. So this thing has no solutions. All right. Next example. Minus 10x is congruent to 12 mod 15. How many solutions? Well, again, this has no solutions. To see that, GCD of minus 10 and 15 is 5, but 5 does not divide 12. Okay. Another example. What about 5x is congruent to 6 mod 11? Okay. So let's compute GCD of 5 and 11 is 1. So by our theorem, how many solutions that are distinct mod 11 should we expect? 1, right? 1. So this has one solution. How do I find that solution? well, I would solve this congruence. But wait, solving this congruence, oh, I'm off screen. Solving this congruence is just solving the congruence anyway, right? So looking at this thing, D is 1, so this is saying that my particular solution is just a solution to AX is congruent to B mod M. So I'm not really helped at all there. It turns out that this solution is X over, or X is 10. So X is equal to 10 here. How do I actually find that in general? You might say, well, you could just check, right? This is mod 11. This isn't too complicated to just try a different, at most you're going to have to try 11 things here. Well, if you started at 0 in this case, it would have been the last thing you tried. But it turns out that X equals 10 is our solution. So I'm going to go over a process for solving this in a little bit, but this is the solution. Okay, another example. So 3x is congruent to 8 mod 10. Well, this has the solution x equals 8. And let's say that you just noticed immediately looking at this thing that 8 works here. So 3 times 8 is 24 mod 10. Sorry, not x equals 8. That doesn't work. X equals 6. Here, let me rewrite this. This looks confusing. Yeah, so x equals 8 doesn't work. That would be congruent to 4 mod 10, not 8. So x equals 6 works. So 3 times 6 is 18. Mod 10, that's 8. So this has solution x equals 6. So maybe you just notice that immediately. You say, oh, well, what do I choose x to be if I want the last digit to be 8? So x needs to be 6. Is there another choice I could make? So in order to rule anything else out without actually having to check, you could just say, well, this is the only one, right? So GCD of 3 and 10 is 1, so that's the only one. So this is the only one that is unique, mod 10. Okay. All right. So what about the next example? One more so that we get multiple solutions. So let's do 9x is congruent to 6 mod 15. Okay. So GCD of 9 and 15 is 3. And of course, 3 divides 6. So this thing is going to have solutions. It should have 3 that are distinct mod 15. So the fact that the GCD divides 6, the GCD is 3, means that I can form a new congruence, which is dividing by 3 here. I get the congruence 3x is congruent to 2 mod 5. Okay. So, what is a solution to this? So this has x naught equals 4 as a solution. So one solution to this new congruence is x naught equals 4. This is actually the only solution to this congruence Okay, so mod 5, this congruence has a unique solution. But of course, I was interested in this congruence mod 15, so I would need to tack on a couple of extra solutions here, mod 15, right? So by the theorem, x is congruent to 4, 9, and 14 mod 15. These are my 3 solutions mod 15. Okay. So, what does this say? Again, forgetting about how I actually found any of these, right? We'll just say that I exhaustively checked and noted that this was the case. So, what did I do here? In the event that I had a GCD that divided B, okay, I could divide both sides of congruence by that and get a new congruence. Solve the new congruence. Okay, in that case, what I get, right, is I'm going to get a unique solution. And you can think about why that is because you're dividing by the GCD, right? So I'm going to get a unique solution, and then, so that's a unique solution mod my new modulus, in this case 5. Okay, but of course I know that the number of distinct solutions mod my original modulus 15 has to be 3. It has to be the GCD. Okay, and so to recover all those solutions, I have to always remember that in mod 15 world I have to add multiples of I have to add multiples here of 5. So why do I know that I'm adding multiples of 5 here? So note 15 over 3 is equal to 5. And these I'm adding multiples of 15 over 3. Okay, I'm adding multiples of this new modulus. Okay. And of course, the reason I'm adding multiples of new modulus is because I'm thinking of this modulus now in mod 15 world, right? So mod 5 world, that's adding 0, so of course you're not doing anything here. But here, I'm going to add multiples of 5 until I go over 15, right? So I add 5, I get 9. I add another copy of 5, so I'm adding 10, I get 14. If I add one more, then I'm over my mod 15. I get brought back to 4 here. Okay. All right, and so that's how that goes. Now, how do I actually solve this in general without saying that I'm exhaustively checking, right? Because that could be extremely annoying if my modulus is anything other than like a really small number. So how do I actually solve this in general? My modulus is a little more complicated. So let's do a fully worked out example here. So so 183 times x is congruent to 15 mod 31. Okay, so we'll see how to solve these congruences. In general, using the extended Euclidean algorithm. So I hope you didn't think we were done using the Euclidean algorithm, because we're definitely not. So I'm going to solve this via the extended Euclidean algorithm. Well, how does that work? You might have guessed that I just look at this thing and I reduce mod 31 so that this makes sense, because 183 is too big. 15 is fine, but I can reduce 183 mod 31. So this is equivalent to 183 mod 31 is 28. So that's 28x is congruent to 15 mod 31. Of course, in general, maybe you have to reduce both sides here. So I begin by reducing everything mod 31. Okay. Now, once I've done that, I change this to a linear Diophantine equation. So this is equivalent to the equation in my proof, 28x minus 31y is equal to 15. Right? And so now I want to solve this linear Diophantine equation. So, and how do I do that? Well, the first thing is I look at the GCD of 28 and 31. So now use Euclidean algorithm to express GCD of 28 and 31. Okay, so quickly dividing by 28, 31 is 1 times 28 plus 3, and 28 is 9 times 3 plus 1, and 3 is 3 times 1 plus 0. So I'm done. Okay, thus, of course, you could say, wait, I can just write out that the GCD of 28 and 31 is 1, but this is how to do it if the numbers involved were significantly nastier. Right, so GCD of 28 and 31 is 1. Okay. So now use extended Euclidean algorithm. Use extended Euclidean algorithm here. So let's write my table. So I have x, y. First entry in the table is 31, so that has an x of 1 and y of 0. 28 is the next entry in the table, that has an x of 0, y of 1. So then 3, just reading off backwards here, this would be 1 minus 1, so that's first row minus second row. That's how I compute that. And then lastly, 1 is minus 9 and 10 in the y column, so that's second row minus 9 times the third row. Okay. All right. So, what does this mean? Thus, 28 times 10 plus 31 times minus 9, I'll write these in parentheses, is equal to 1. Or, i.e., 28 times 10 minus 31 times 9 is equal to 1. Ah. Now you see where I'm going with this. Well, look at what we did, right? We recast this congruence as the equation 28x minus 31y is equal to 15. And what we have here is 28 times 10 minus 31 times 9 is equal to 1. So I have exactly what I want here, so long as my right-hand side is 15. So I multiply both sides of this expression by 15, and I'm going to, of course, gather those multiples of 15 in the 10 and 9 slots here, right? And so multiplying by 15, I get 28 times 150 minus 31 times 135 is equal to 15. Okay. So, thus 28 is congruent, or sorry, let me give myself room here. I'm running out of real estate here to write this. Thus, 28 times 150 is congruent to 15 mod 31. Why can I say that? Going back here. Right. I have this linear combination involving 31 here, but of course, viewing 15 as a linear combination of 28 and 31, mod 31, 31 is 0, right? So 31 is 0 mod 31, and so what's left is 28 times 150. So 28 times 150 is congruent to 15 mod 31, i.e. x equals 150 is a solution to the congruence 183 times x is congruent to 15 mod 31. Okay, thus, let's reduce mod 31. So reduce mod 31, you get 26. So x equals 26 is a solution. It's not just a solution, it is unique mod 31, since the GCD of 28 and 31 is 1. Okay. Now, of course, if the numbers involved are not too big, then you wouldn't have to go through this whole process. But this is showing you how you would do it if the numbers involved were nasty, right? So if I gave you like a bunch of 3 or 4 digit numbers, you're not going to brute force try a bunch of things, right? I could give you a congruence mod, 1371, and if I've arranged it in such a way that the GCD of what I'm multiplying x by and 1371 is 1, then there's a unique solution for that congruence, but you're not going to check 1371 values of that thing, right? You're just not going to do that. So anyway, so this is showing you how you would go about this process in general. So don't worry, you are going to have plenty of practice solving these congruences, because I'm going to assign them as homework. So I will post your third homework later today. It'll be due next Monday. On Monday, when it's due, I will post your fourth homework, and it will be due the Friday after that, and on that Friday I will post your second exam. So there's going to be a chain of assignments that are assigned on the same day that the last one's due, or that the previous one is due. So, and that starts today. So today I will assign your third homework. Okay. So how how does this relate to what I want to talk about next? So the next immediate thing that I want to do is discuss multiplicative inverses in the mod world. So we say that integers a and b are multiplicative inverses So we say that these are multiplicative inverses mod m if a times b is congruent to 1 mod m. Okay. Of course, when there's no danger of confusing what it is that's going on here, we don't have to actually specify that they're multiplicative inverses. We could just say that they're inverses. So as I've mentioned, and as some of you might know, if you have any experience with some basic algebraic structures, so for instance groups, but specifically groups, rings, fields, you know anything about those types of things, then you know where this discussion is heading, and you might have already figured out, what sorts of things you might assume about M in order to guarantee that you always have multiplicative inverses. Anyway, how does this relate to what I just did? Note finding a multiplicative inverse of A is solving the congruence AX is congruent to 1 mod M. Okay. So if I ask you to find a multiplicative inverse mod M for a given A, that's really me asking you to solve this congruence. Going back to the theorem, of course, this tells you exactly something that is required before you have any hope of being able to do this. So another corollary of my big theorem in this section is the integer A has an inverse mod M if and only if the GCD of A and M is 1. Obviously. Because the GCD of A and M has to divide B in this expression for it to have a solution at all. And that's saying that the GCD has to divide 1. So, well, if the GCD has to divide 1, then clearly it has to be equal to 1. So the GCD of A and M has to be 1 for this to work at all. Right? Okay. And so here's an example. So find all multiplicative inverses of 13 mod 100. Now I intentionally wrote this out in a stupid way. So I phrased this as find all. Right? But of course, by this previous corollary, how many of them are there? Well, 1, right? If the GCD is 1, there's always guaranteed to be a single unique one mod 1, mod 100 in this case. So this all multiplicative inverses is the inverse. of 13 mod 100. So looking ahead to, if you're wanting to show some fact about an algebraic structure supposedly defined by, modular arithmetic, this is showing the uniqueness of inverses, right? Which is an important thing. Okay, so what is this? The multiplicative inverse of 13 mod 100. This means I need to solve the congruence 13 times x is congruent to 1 mod 100. Okay, oh, I'm off camera. So 13 times x is congruent to 1 mod 100. This, of course, is equivalent to the expression 13x minus 100y is equal to 1. Okay, what is the GCD of 13 and 100? The GCD of 13 and 100 is 1. Okay, so find via Euclidean algorithm, because you're going to use that later. Okay, so finding via Euclidean algorithm, if I write this out, so 100 is 7 times 13 plus 9. 13 is 1 times 9 plus 4. Next is 9. 9 is 2 times 4 plus 1. And lastly, 4 is 4 times 1 plus 0. Okay. So continuing this example on the next sheet. So using extended Euclidean algorithm, what do I get here? So my table looks like this. So 100 has x of 1, y of 0. 13 has x of 0, y of 1. So I'm not going to write all these things out. So 9, 4, and 1 has a table, if you go through the extended Euclidean algorithm, of 1 minus 1, minus 1, 8, and 3, minus 23. Okay, so then this last line tells me that 1 can be expressed as a linear combination of 113 in the following way. This is 100 times 100 times 3. So 100 times 3 minus 13 times 23. Okay, and you can just check that that actually works. Thus, 13 times minus 23 is congruent to 1 mod 100. So the multiplicative inverse of 13 mod 100 is minus 23. Of course, using the least non-negative residue, minus 23 is congruent to 77 mod 100. And we'll go ahead and make a blanket statement that when I am asking you to solve a congruence or to make a statement in some congruence world or some mod M world, the answer I want is always the least non-negative residue. I'm not going to take off points if you wrote minus 23 there and left it as that mod 100, but typically it is preferable to use the least non-negative residue. Okay. All right. And so there are a couple other examples I'm not going to go over of how you can kind of quickly use the extended Euclidean algorithm to do this. So if you want to go over those methods, you can have a look on page 134. What I will say is the following. So here's quick kind of table for what to do, how to solve this. So, solving AX is congruent to B mod M when the GCD of A and M is equal to 1. Okay, well, what if so the first thing you say is, what if the GCD of A and M is not 1? Well, this process is going to work to find a single solution, and then finding the rest of them, of course, is just going to be adding multiples of the reduced modulus, right? So actually, if you know how to solve this when the GCD is 1, then you know how to solve this in general. What do I mean by that? So in the process of solving these congruences, let's say that your GCD is not 1. Let's say your GCD is some number bigger than 1. Let's say your GCD is 5, right? The idea is that in the congruence that you're solving, you can divide by 5 to get another congruence. That congruence is set up in such a way that your new A over D, right, or A over 5 in this case, is going to have GCD 1 with the new modulus, which is M over 5, right, or M over D. Okay, so that new congruence is a congruence where the relevant GCD is 1. And so you can use this process. And then using this process, you can recover all the solutions in your mod M world from the mod M over D world just by adding multiples of M over D. Okay, so that's how this works. So actually, you only need to understand this and that one extra step, okay, to get you there. All right. So, first, form the linear Diophantine equation AX minus MY is equal to B. And secondly, use the extended Euclidean algorithm to find x naught, y naught such that a x naught minus m y naught is equal to 1. And then 3, compute x, which is congruent to, just since you're looking mod m here, you're computing x, which is congruent to b times x naught mod m. Okay. Okay. You can do that, of course, by where does this b times x naught come from? In that process we use, at this step, we multiplied both sides by b. Since we're looking mod m, this term on the left here involving the m is 0. And so a times b times x naught is congruent to b mod m. Okay, that's why this works. Okay, and I only need one extra step here, that is adding multiples of m over d if my d is something that's not 1. Okay. And so this is also, so I can use the same process to find inverses, but this is the important bit. Okay, so that's the important bit. Okay. So now, in the time that's remaining, I want to set up my statement of the Chinese remainder theorem so that tomorrow I meant to finish chapter 6 today, so it's going to take me an extra like 20 minutes at the beginning of lecture tomorrow before I can move on. But this is the This is the idea here. If you're confused by solving these congruences, then during this week's office hours, I can do a few more examples of that. So, okay. Last thing I want to talk about for congruences right now is the Chinese remainder theorem. So before I get to the actual statement of the Chinese remainder theorem, I have a question. So my question is going to pose, seems like a weird question at first. I want to find a number that has a bunch of different remainders when divided by different numbers, okay? But it's the same number, so it's a number x, but when I divide it by 2, 3, 5, I get a list of different remainders, and so I want to know, can I determine x using congruences, of course. I understand that there may be more than one integer satisfying this. I mean, in fact, I understand there's going to be infinitely many integers satisfying this, but I want to be able to find the integer that when I divide it by the list of divisors that I give, I get the list of remainders, okay, that I specify. So that I'm not just saying a bunch of words here, I'm going to give some specific examples. So suppose, or I should say, what is a number x such that I have a remainder of 2 when I divide x by 3, a remainder of 3 when I divide x by 5, and a remainder of 2 when I divide x by 7. So I'm looking for an integer x such that when I divide it by 3, I have a remainder of 2. When I divide it by 5, I have a remainder of 3. And when I divide it by 7, I have a remainder of 2. Well, you immediately recognize that whatever x is, it satisfies a system of congruences. So the answer here is whatever x is, it must satisfy a system of congruences, right? Okay, so that system of congruences is x is congruent to 2 mod 3, and x is congruent to 3 mod 5, and x is congruent to 2 mod 7. Okay. All right. And so really this question is a question that is asking how to solve systems of congruences like this. Okay. And so it turns out that this is the subject of the Chinese remainder theorem. So the idea of the Chinese remainder theorem is that I have a list of congruences. My list of congruences look something like this. And the idea is that I can, under the right circumstances, say that I can find an X satisfying this list, this system of congruences. That is, X satisfies this property that, when I divide it by this list of divisors, I get the specified remainders, right? And so X being a solution means that simultaneously all of those things are true about it. So that's all I wanted to say for today. So during tomorrow's lecture, I will actually state a preliminary theorem and prove it, and then state the Chinese remainder theorem and prove it. It won't take too long, probably about 20 minutes of tomorrow's, the first 20 minutes of tomorrow's lecture will be devoted to stating and proving Chinese remainder theorem. And after that, we'll move on to the next block of material. So like I said earlier, I will post your third homework assignment soon, so later this evening today, and that'll be due next Monday. And your remaining, so right now you have, I think last I checked, your first homework's been graded, homework 2 and your exam should be graded soon. So anyway, I will post an announcement when I've posted your third homework. So that's that. I'll see you all tomorrow.